So let's look at some practice problems with combinations, or about combinations with repetition. As all of these links down below to the next problem, there are a total of 6 in here. I will present the problem, give you a chance to pause the video, unpause it, I'll put up the numerical answer, and if you get it, click the link to the next problem. If you don't get it, I'll show a fully explained solution and then go on to the next problem. Example 1. A school has 100 students, each of whom sign up for one of 4 elective classes: art, music, home ec, or shop. How many unique class sizes can a school have for electives? And how many unique class sizes can a school have if each class has at least 20 students enrolled? Pause the video, take a few minutes to solve. Alright, the solutions are 176,851 and 1,771. Here's how. In this problem, each of the there are 4 distinct things that I'm selecting, so n equals 4, and I'm selecting those classes 100 times. The students are sort of interchangeable in this example because I'm only caring about class size, not who's in the class. So each one of these students just selects one of these classes, and we see what we have. So in this case, for the first problem, R is going to be 100. And then I follow through the formula, so I do 4 plus 100 minus 1 over, not over, sorry, choose 100. Again, what happens here is we have 100 students. That's not 100, that's 6, but you know what I'm getting at. I need to split into 4 groups, which means I need 3 dividers. So I have 103 objects, and I need to choose the location of the 100 students. Or you can look at it as 103 factorial over 103 minus 100, 3 factorial times 100 factorial, because I have 103 objects here, 100 students, 3 dividers, and I can, when I permute all of them, when I get the rearrangements of them, I divide by this because that's the number of ways to permute 3 objects, and divide by this because that's the number of ways to permute 100 objects. And when I do that calculation, I will get 176,851. Down here, how many unique class sizes can the school have if each elective class has at least 20 students enrolled? So the only big difference here is I'm first going to ensure that I have 20 students enrolled in each class, and that's 20 students times 4 classes. 80 students need to be enrolled to begin with, so I will end up with 20 students left over to choose the various classes. So instead of moving all 100 students around, I'm going to move just 20 students around. 20 students are going to now make the choice. And so what we end up with is still 4 classes, so n is still 4 distinct things. 4 plus 20 minus 1, choose 20 for the students, which is 23, choose 20, 23 factorial over, sorry, wrong order on there, 3 factorial, 20 factorial, and when I do that computation, I will get 1,771. Okay, example 2. You are playing a game in a 3-dimensional playing space. During each turn, you have 3 choices for moving 1 step: forward, right, or up. How many possible locations can you reach at the end of 10 turns? Pause the video, try to solve this. Okay. At the end of 10 turns, assuming you have to make a move each turn, there are 66 possibilities, and here's why. It doesn't matter if I look at 2 turns. It doesn't matter if I go right up or up right. I end up at the same thing, same spot. So the locations are just determined on how many times I move forward, how many times I move right, and how many times I move up. Those are the distinct things. So in here, n is 3. And I choose to move either forward, right, or up 10 times. R equals 10. And I can just go through the formula now. 3 plus 10 minus 1. Choose 10, which is going to be 12, choose 10. 12 factorial over 12 minus 10, 2 factorial, 10 factorial. In here, the 12 and the 10 is the biggest one. 12 is 2 bigger than that. So this will be 12 times 11 times the 10 factorial here. And the 10 factorial here cancel. I'm left with 12 times 11 divided by 2 times 1. I would reduce this down, 12 divided by 2, and get 6. So I have 6 times 11, which is, of course, 66. Just like that. All right. Example 3. A teacher wants to make a test that has 15 questions on it. Each question can either be a multiple choice question, a short answer question, or an essay question. How many different formats can a test have if it starts with all multiple choice questions, followed by all short answer questions, and finally all of the essay questions? Pause the video, take a little bit of time to solve this. Okay, there are 136 possible formats for this test to have. And the reason? There are 3 distinct objects I'm choosing. I will either, for each question, choose to have multiple choice question, a short answer question, or an essay question. So n will be 3. Those are the distinct things. Now, since I didn't say like question 1 is in any way fundamentally different than question 2, beyond a very slight thing that I can't like go backwards. I can't have question 1 be a short answer and then question 2 be a multiple choice. But beyond that, there's no distinction. If question 1 and question 2 are multiple choice, I don't care which problem ends up in both of those. It's the same format for this test. So for that reason, I will just choose these 3 types 15 times and just use the formula. N plus R minus 1, 3 plus 15 minus 1, choose R, 15, which is 17, choose 15, which will be 17 factorial over 17 minus 15, 2 factorial times 15 factorial. As always, I look to see which one's bigger down here. It's the 15. That will cancel out most of the stuff from the top. So 17 is 2 more than 15, so that's 17 times 16 times 15 factorial, because it would keep going down, divided by 2 times 1 times 15 factorial. Those cancel. And then 17 times 16 over 2 times 1, I will reduce down this, 16 over 2. So you get 17 times 8, which is 136. Example 4. How many solutions does the equation x1 plus x2 plus x3 equals 9 have if xi is an integer and xi is greater than or equal to 0 for all I in 1, 2, and 3? Okay, so we want to figure out how many integer solutions, and one integer solution would be something like 0 plus 0 plus 9. Or 9 plus 0 plus 0 is a different integer solution. We also have 1 plus 2 plus 6, or 3 plus 3 plus 3. So lots of different things. Pause the video, try to solve it. And here's the solution, 55. Here's how we do this. So in this, there are really 3 distinct objects, either x1, x2, or x3. So n is 3. I will choose numbers to be in those objects 9 times. Each number, so if I want integers, I can split this into 9 ones. And each one of these ones will either be part of x1, part of x2, or part of x3. I can't split any differently or any deeper because I need to stay in the integers. And I go all the way down to 1s because if I have a 2, that's the same as splitting it up into 2 different 1s. So moving a 2 into a variable is the same as moving 2 1s. And you can think of it this way. So I have these 3 things and I have all these 1s. And I have to divide it into 3 things. That means 2 dividers. So the answer I said of, let's say, 1 plus 2 plus 6 just looks like this. I have a 1 divided, then I have 2 1s divided, and then I have 6 1s. And you can see that any permutation of these goes uniquely to an equation. So if I just put, let's say, 1, 2, 3, 4, 5, 6, 7, 8, 9, I'll put a split here and a split here. This would be x1 is 4, x2 is 1, x3 is 4, 4 plus 1 plus 4 equals 9. And any x1, x2, x3 can go uniquely to a permutation of that. So they're measuring the same thing, which is this same problem we've been dealing with combinations with repetition. So I will just do same formula, n plus r minus 1, 3 plus 9 minus 1, choose r, 9, which is going to be 3 plus 9 is 12, minus 1 is 11, choose 9, 11 factorial, 11 minus 9 is 2 factorial, times 9 factorial. The 9's bigger, so I will reduce this down. 11 is 2 bigger than 9, so I have 11 times 10. And then I'm left over with, not 19, 9 factorial. In the bottom, I have 2 times 1 times 9 factorial. 9 factorials cancel. 10 over 2 times 1 is 5, so I get 11 times 5 equals 55. Example 5. How many solutions does x1 times x2 times x3 equals 2048 have if xi is a natural number for all I in there? Pause the video, take a few minutes to try to solve this. Alright, the solution is 364. And here's why. 2048 is a power of 2. The prime factorization of this is 2 to the 11th. Or basically 2 times 2 times 3 times 4 times 5 times 6. Okay. So figuring out how to multiply 4 natural numbers, no negatives, up and get up to this is the same as sort of assigning a certain number of 2's to be in each of these. So each of the 2's can select one of these 4 spots. And just like the last one, n will be 4, and r will be 11. Now, it should have made a lot of sense with addition, but someone's going to say, hold on. If I try to split these up, so I'll put 11 2's, and I split it up like this. So let me grab a few things. So I need to split into 4 things, which means 3 dividers. So I can put 1, 2, let's put a third one here. Okay. So we see 2 times 2 times 2 is 8. 2 times 2 times 2 times 2 times 2 times 2. 2 to the 6 is 64. 2 times 2 is 4. So 8 times 64 times 4. That will give me 2048. But hold on. What's going on here? Because if I multiply this by 0, then I'm going to get to 0. That's not what's happening here. We're doing powers of 2, not just sort of adding things up. So if there are 0 2's here, that's really 2 to the 0, which is 1. And multiply this through, and you will still get 2048. So the fact that you have no 2's going to one of these means that it's 2 to the 0 power, not 0. Okay. N is 4, r is 11. Let's dive right in, get the answer. So n plus r minus 1, 4 plus 11 minus 1, choose r, 11, is going to be 14, choose 11, 14 factorial, 14 minus 11 is 3 factorial, 11 factorial. 11 and 14 are going to reduce down. 14 is 3 bigger than 11, so I get 14 times 13 times 12 times the 11 factorial, which is going to cancel. 3 times 2 times 1 times the 11 factorial, which cancels. And in here, 3 times 2 times 1 is 6. This will reduce down. Multiply it together, I get 364. All right, last example. 4 friends go to a hamburger shop. Each friend orders either a hamburger, a cheeseburger, or nothing. How many different orders are there? Where an order is unique solely on the quantity of each thing ordered and not on who orders what. So this is like the first example from the last video. Pause it. Feel free to try it. And the solution is 15 different orders. And here's why. There are 3 unique possible orders. I'm assuming that these friends are not ordering more than one thing. They aren't ordering 2 hamburgers or 2 cheeseburgers. That would be a different problem. So 3 distinct objects, either hamburger or cheeseburger or nothing. I'll consider nothing a distinct order. That's n. There are 4 friends. That's r. And so we just go through and say, okay, I have 4 friends. I need to split them into 3 groups, which means 2 dividers. So either follow the formula and do n, 3, plus r, 4, minus 1 over, choose r, which is going to be 6 choose 4, which is 6 factorial over 6 minus 4, 2 factorial, 4 factorial. 6 and the 4 reduces down the most. 6 is 2 bigger than 4, so I have 6 times 5 before I get to the 4 factorial to cancel. 2 times 1 times 4 factorial cancels. 30 divided by 2 is 15, which is the same thing as saying I have 6 total elements. There are 4 repeated people and 2 repeated dividers to split this into 3 groups. Alright, leave a comment with any questions, and I have one more video that's going to come up shortly about counting and Catalan numbers.